Hey there. Welcome. Let's just jump right in, shall we? Have you ever stopped to wonder what is actually happening inside the device you're using to listen to this right now? I mean, really happening. From the microscopic atomic level, all the way up to the exact logic gates powering your screen, today's explainer is taking us on a truly fascinating journey. We are going to completely demystify semiconductors, which are, without a doubt, the fundamental building blocks of modern electronics.
Okay, let's quickly look at our roadmap for today. First, we'll cover what semiconductors actually are. Then, we'll talk about doping, specifically N and P types. Third, the PN junction diode. Next up is forward and reverse biasing. And finally, we'll wrap up with real-world applications. Step by step, we're going to build this knowledge together.
All right, Section 1. What are semiconductors?
To really get this, at the most basic level, we have to ask how materials conduct electricity in the first place. Some materials are incredibly good at it, and others don't do it at all. Think about conductors, like copper. They have extremely high conductivity and essentially a zero energy gap. Then you have insulators, like rubber, which have extremely low conductivity and a massive energy gap. But semiconductors? They sit right there in that perfect, highly adaptable middle ground. And what's really wild is that at absolute zero temperature, pure silicon behaves literally exactly like an insulator, zero free charge carriers. But its moderate conductivity can be cleverly controlled by simply raising the temperature, hitting it with light, or adding impurities. That last one is a process called doping, which we'll get to in just a second.
Now, if we think about the energy bands at play here, we can see exactly why this happens. For an electron to actually conduct electricity, it has to jump from the lower valence band up to the conduction band. In a conductor, those bands basically overlap. It's an easy commute. In an insulator, that gap is way too huge to cross. But in our semiconductor, right in the middle, electrons just have to make this microscopic leap across a really small energy gap of roughly 1 electron volt. Just give them a tiny push of energy and they can make that jump.
Moving right along, let's get into Section 2, doping, specifically N and P types.
So pure intrinsic semiconductors are super interesting, right? But honestly, they aren't quite conductive enough on their own to run a supercomputer. And that brings us to doping. Doping is simply the process of adding a very, very small amount of a specific impurity into a pure semiconductor. This creates what's called an extrinsic semiconductor, and it vastly increases its conductivity. Basically, we are intentionally introducing a tiny calculated flaw to radically alter and control how the material handles electricity.
By choosing a very specific type of impurity, we can get completely different results. It's like a giant atomic puzzle. With an N-type semiconductor, we've doped the pure silicon with a pentavalent impurity, something like phosphorus. Pentavalent just means it has 5 valence electrons, but the silicon crystal structure only needs 4 to bond, so you end up with this 5th extra electron that's just kind of loosely hanging around. It becomes a free electron, a negative charge carrier. On the flip side, with a P-type semiconductor, we use a trivalent impurity, like boron, which only has 3 valence electrons. This creates a literal deficiency in the crystal structure, a vacant parking spot that we call a hole. And this hole acts exactly like a positive charge carrier. So to keep it simple, N stands for negative electrons as the majority, and P stands for positive holes.
Which brings us to Section 3, the PN junction diode.
Okay, so we've got our negative building blocks and our positive building blocks. What actually happens when we physically smash an N-type and a P-type block together? Well, it creates an absolute microscopic traffic jam. Step 1, because opposites attract, the free electrons from the N side immediately try to diffuse over to the P side, while the positive holes from the P side diffuse right over to the N side. Step 2, as they cross the border, they meet and recombine right there near the junction. The electrons essentially just fall into the holes. But here is the catch for Step 3. When they recombine, they leave behind these charged, immobile ions that are locked in place. So this initial rush of charges rapidly builds a physical barricade right at the border that entirely stops any further flow.
And that barricade is what we call the depletion region. It is completely 100% devoid of any free charge carriers. It's just a solid wall of positive and negative immobile ions. This reveals a pretty profound reality about the physics here. This newly formed depletion region acts entirely like an insulator. Because of this wall, without any outside help, a standard PN junction diode naturally blocks the flow of electricity.
So how do we fix that? Let's look at Section 4, forward and reverse biasing. Since an unbiased diode acts like a literal brick wall to current, we need a way to take control of it. Enter biasing. Biasing is just the application of an external battery voltage to command our microscopic traffic system. And we have two main ways to hook up that battery, with wildly different results. In forward bias, we connect the positive terminal to the P side and the negative terminal to the N side. This setup pushes charges toward the junction. The depletion region narrows, the barrier drops, and current flows super easily with very low resistance. It's basically the green light. But if we completely flip the battery around for reverse bias, negative terminal to the P side, positive to the N side, we actually pull the charges away from the junction. The depletion region widens, creating an impenetrable wall of high resistance that blocks the majority of charge carriers from crossing at all.
This entire process essentially turns the diode into a one-way valve for electricity. Think about how the current reacts. In the forward bias region, you increase the voltage just a little bit, and then boom, the forward current absolutely skyrockets upwards. But in reverse bias, you can increase that reverse voltage quite a bit, and the reverse current essentially flatlines. Only a tiny, negligible trickle gets through. The valve is shut completely tight.
Now notice I said you have to increase the voltage a little bit first. The forward current doesn't skyrocket immediately. It needs a tiny initial electrical push to overcome that depletion barricade we built earlier. We actually call this the knee, or cut-in voltage. For a diode made of silicon, that exact minimum push is about 0.7 volts. For germanium, it's about 0.3 volts. But the moment you cross that very specific threshold, current flows freely.
All right, Section 5, Real-World Diode Applications.
We've spent a lot of time in the microscopic, theoretical world of electrons, holes, and energy gaps. Now let's look at the macro applications, the real so what of our explainer today. First up is the rectifier. This is an electronic circuit utilizing our diodes to convert alternating current, or AC, into direct current, DC. Because the diode only lets current flow easily in one single direction, it acts as the absolute perfect electrical filter. So, whether it's a half-wave or a full-wave rectifier, it takes that wavy, back-and-forth AC power coming right out of your wall outlet, and it forces it into the steady, one-directional DC power that your phone or laptop charger actually needs to function. Pretty cool, right?
But let's see how this builds into computation. By arranging these simple one-way diodes alongside a few resistors, we can literally create high-speed digital logic gates, the AND, OR, and NOT gates. By combining high and low voltages, which directly represent our binary ones and zeros, these simple diode circuits process information. They're making the fundamental logical decisions happening millions of times a second inside the processor of whatever device you're using right now.
Now, for a bit of a plot twist, the Zener diode. Remember just a minute ago when I said reverse bias throws up a wall and blocks current entirely? Well, the Zener diode is heavily doped and specially designed to completely break those rules. It's literally meant to operate safely in that normally blocked reverse breakdown region. When the reverse voltage hits a specific limit, known as the Zener voltage, it suddenly lets current through, which magically keeps the voltage output perfectly constant. It acts as an incredible voltage regulator, protecting your delicate circuits from wild power fluctuations. And a list of applications just keeps going. Those exact same PN junctions are used to create light-emitting diodes, or LEDs, converting electrical energy directly into the light on your screens or the bulbs in your home. They are the entire basis of solar cells, doing the exact reverse and turning sunlight back into electricity. We use them for photodiodes, voltage regulators, extracting audio signals and radios through demodulation, and crucial electrical protection circuits. Just adding a tiny impurity to a piece of pure silicon cascades into an entire technological revolution that quite literally lights up our world.
So, we have traveled from the basic atomic structure of an insulator all the way to the incredible one-way valves that regulate our power and compute our data. From a single microscopic electron hole to the exact logic gates powering the screen you are looking at right this second, the possibilities are just endless. It all starts right here. What will you build with these basic blocks of physics? Thanks so much for joining me on this explainer, and keep exploring.